I now have the tremendous privilege to introduce the first of our distinguished scientific talks this afternoon. It's a talk from last year's Nobel laureate, Professor Kip Thorne from the California Institute of Technology. And for those of you who perhaps don't follow the Nobel Prizes every year, you may well have seen the work of Kip Thorne in the movie theatre, because the scenario of the film Interstellar was based on some earlier work by Professor Kip Thorne, which was beautifully converted into one of the classic science fiction movies so far this century. I won't go any further into introducing Professor Thorne. He's asked me to keep his biography short. The screen is now down, so just join with me in welcoming Professor Thorne to the stage. I hope all the sound is correct. So,
could we have the lights completely off, please? The lights completely off and the image filling the entire screen. 1.3 billion years ago, when here on Earth multicelled life was just forming and beginning to spread over the globe, but in a galaxy far, far away, two black holes circled around and around each other. This is what it would have looked like to your eyes if you had been there. This is based on a computer simulation of what was seen by our gravitational wave detectors. Two black holes circled around and around each other, emitting ripples in the fabric of space and time called gravitational waves. And as those waves traveled away, they kicked back and forced the black holes to spiral closer and closer together until in a gigantic cataclysmic collision, they emitted in gravitational waves as much energy as you would get by annihilating three suns and turning that all into gravitational wave energy. That gravitational wave energy traveled outward from the galaxy in which the black holes lived into intergalactic space, across the great reaches of intergalactic space, and 50,000 years ago, when our ancestors were sharing the Earth with the Neanderthals, think of that, 50,000 years ago, this burst of gravitational waves reached the outer reaches of our Milky Way galaxy. It traveled onward to the Earth, arrived at the Earth initially at the tip of the Antarctic Peninsula, traveled upward through the Earth, completely unscathed, and emerged at a gravitational wave detector called LIGO in Livingston, Louisiana. 7 milliseconds later, emerged at the gravitational wave detector in Hanford, Washington. And the signals then went out into a computer and were displayed for the LIGO collaboration, LIGO-Virgo collaboration of scientists to see within a matter of minutes. And that collaboration of 1,000 scientists around the world in about 22 different nations. That collaboration analyzed the data very carefully. The signal was almost too good to be believed, but after a few months of analysis, the collaboration, became convinced this was the real thing, and we announced it to the world on February the 12th in 2016, and that immediately made front page headlines in all the major newspapers around the world. How did we get here? Let me tell you the story in brief of the creation of these gravitational wave detectors and how it's the seeds for it lay with Albert Einstein. So the story begins with Albert Einstein in 1916, precisely 100 years before our announcement of the detection of gravitational waves. Einstein had just developed his general theory of relativity, which says that gravity is caused by a warping of space and time. And he used the mathematics of his general relativity theory to predict the existence of gravitational waves. And what his mathematics told him was that if you were to place a number of of particles out in space in a rectangular grid like this, and a gravitational wave came by traveling through the screen, that gravitational wave would stretch and squeeze those particles, each of them moving inertially, stretch and squeeze them along the horizontal and vertical axes, perpendicular to the propagation direction of the waves. We can think of this as being that either inertial reference frames that are far away move back and forth with respect to each other, or that space itself is being stretched and squeezed. I prefer that description. Albert Einstein also said in his marvelous paper in 1916 that the waves were predicted to be so weak by the time they reached the Earth that humans would probably never ever be able to see them. Nevertheless, roughly 50 years later, Joseph Weber at the University of Maryland sat down, designed and built the first generation of gravitational wave detectors. Why did he have the chutzpah to do this? Because the world of science had changed. We had learned about black holes and neutron stars that Einstein never knew about. It was clear that they would be marvelously strong sources of gravitational waves, and the laser and computers had been invented as new tools that could be used in technology to design detectors of far better precision than Einstein had ever imagined would be possible. I myself learned about gravitational waves from Joseph Weber at a summer school in the French Alps in Les Ouches, France. And shortly thereafter, I moved to Caltech on the faculty, where I started to build a theory group working on black holes, neutron stars, and gravitational waves. And we began to think about what you could do with gravitational waves if you could possibly detect them. And let me describe our thoughts from that era in terms of the contrast between electromagnetic waves and gravitational waves. So electromagnetic waves from astronomical objects are oscillations of the electromagnetic field that propagate through space-time, while gravitational waves are oscillations of the very fabric of space-time itself. Electromagnetic waves are incoherent superpositions of emission from individual particles, atoms, and molecules, whereas gravitational waves are emitted coherently by the bulk motion of large amounts of mass or energy. Electromagnetic waves are all too easily absorbed and scattered by matter between us and the source, whereas gravitational waves are never significantly absorbed or scattered. Even if they're emitted in the Big Bang, they aren't absorbed or scattered by the very hot, dense matter of the early universe. As implications, many gravitational wave sources won't be seen electromagnetically, and that was true of the first gravitational waves that we saw from these colliding black holes. There was no electromagnetic emission seen whatsoever, no light, no radio waves, no X-rays. And huge surprises are likely because our current knowledge of the universe, at least as before we saw the first gravitational waves, was based almost entirely on light, X-rays, and other electromagnetic radiations. And gravitational waves are so radically different from electromagnetic waves that we will see very different aspects of the universe, and there should be major surprises. In 1972, the same year as we began to, in my group, to develop a vision for the science we could do with gravitational waves, Rainer Weiss at MIT, a young professor at MIT, developed an idea for a new type of gravitational wave detector in which he had mirrors that hang from overhead supports by wires, separated by distances that can be many kilometers apart. When the gravitational wave comes by, it pushes these mirrors apart, pushes those mirrors together, and then a half a cycle later pushes these apart and these together. And a technique using laser beams called interferometry. Laser interferometry is used to monitor those motions. A laser light comes in through a beam splitter, goes into an optical cavity between these two mirrors, resonates inside back and forth between those mirrors about 100 times, and similarly over here. And then the light comes back, recombines, and goes toward a photodetector, which monitors the rising and falling intensity, which tells you about the rising and falling shape of the gravitational wave, the motion of the arms apart, the mirrors apart in this interferometer. Now, I looked at the ideas that Ray presented just in a great rush, just as I was finishing with colleagues a textbook called Gravitation. And it seemed to me that Ray was either crazy or stupid or something, that this was really, no way this was ever going to succeed. And so in this textbook, I actually wrote down that this is not very promising. And why did I say that? Let me give you some numbers. So we're beginning, say, with 1 centimeter. If we divide by 100, we get the thickness of a human hair, 100 microns. Divide by 100, we get the wavelength of light, 1 micron. Divide by 10,000, you get the diameter of an atom. Divide by 100,000, you get the diameter of a nucleus of an atom. You divide by 100, you get the magnitude of the motions of the mirrors back and forth as predicted for the sources of gravitational waves that my theorist colleagues and I were thinking about at the time. That is just so unbelievably small that I didn't see how you could possibly do that. You're trying to monitor the motion of a mirror with light at a level that is approximately 1/1,000,000th the wavelength of the light. And that just seemed to be totally crazy. However, after a series of long conversations with Ray Weiss and with Vladimir Virginsky in Moscow, and studying Ray's 1972 paper on his idea, in which he laid out and identified all the major noises, types of noise that these gravity wave interferometers would have to face. And he explained how to deal with each and every one of them and computed what sensitivity you might be able to achieve. After that, I became convinced. And I wound up spending the rest of my career doing everything I could to help Ray and his experimental colleagues pull this off. Let me explain just with one source of noise why I became convinced. As I told you, we were predicting that the mirror would be pushed back and forth by an amount of 10 to the minus 17 meters, 100 times smaller than the nucleus of an atom, 100 times smaller than a proton. And so Ray said, when you bounce the light back and forth in here 100 times, so the signal gets 100 times bigger, and so now we're having a signal of about 10 to the minus 15 meters. Then laser light has the marvelous property that's very smooth if you have lots of photons in it. But the fact that light is made up of discrete photons means that when the light comes to the photodetector, it comes with photons coming in, not absolutely smoothly, but with random arrival times. And you can show that the magnitude of the motion you can measure in the presence of that randomness of the arrival times of the photons is the wavelength of the light divided by 2 pi, and 1 over the square root of the number of photons you use in a measurement. And so the business is just simply to use a lot of photons. 10 to the 18 photons, that's what you wind up using if you have, say, a 30-watt laser. And so the square root of 10 to the 18 is 10 to the 9, so you get a 10 to the minus 9 on top of a 10 to the minus 7 meters. And the noise level is 10 times lower than the gravity wave signal. So that means, if you're very naive, that sure, you can do it, but in reality, doing it in practice at this level of precision is absolutely exceedingly difficult, and I'll highlight that difficulty a little bit later. And there is not just this source of noise, but there are huge numbers of other sources of noise. But thanks to light as our key tool in LIGO, the project ultimately had success. 1976 to 78, then we made a decision to create a gravitational wave experimental group at Caltech. We brought Ronald Drever from Glasgow, where he had invented several very important improvements on Ray Weiss's ideas. And at Caltech, under Ron's leadership, the Caltech team that we created a 40-meter prototype gravity wave detector, 1% of the length of the detectors that we ultimately would have to use in LIGO. In the meantime, at MIT, Ray Weiss and his group had completed a 1.5-meter prototype detector and had carried out in 1980 to 83 a feasibility study for a kilometer-scale gravity wave interferometers. Based on the MIT feasibility study of Ray Weiss and the prototypes, not just at Caltech and MIT, but really excellent prototypes in Glasgow, Scotland, and the Max Planck Institute for Astrophysics in Germany. In 1984, with the encouragement of the U.S. National Science Foundation, we created LIGO as a MIT Caltech collaboration under the leadership of Ray Weiss, Ron Drever, and me. We were the most dysfunctional leadership that science has ever seen. We brought on Robbie Vogt, who had been the first chief scientist of the Jet Propulsion Laboratory for planetary missions, as our director in 1987. And under his leadership, we wrote a proposal to construct LIGO, first facilities, then a two-step in which the laser beams would go back and forth, large vacuum systems. Then a two-step strategy in which we would build initial interferometers at a sensitivity where we would have to be very lucky to see gravitational waves. And then more advanced interferometers at an improved sensitivity where we would be likely to see lots of gravitational waves. So that was our strategy as we laid it out in 1989. We had a bit of trouble getting this funded because we were saying that we were not going to see anything with our first gravity wave detectors. But ultimately, the National Science Foundation in 1992 and the US Congress bought into this. And they backed us continually ever since. And I have to give great credit to the Congress, Republicans as well as Democrats, and to the National Science Foundation for that backing over a period of several decades. We brought on Barry Barish, who had experience running large high-energy physics projects in 1994 to lead the construction of these interferometers. And he expanded LIGO to other institutions so that it's now 1,200 scientists and engineers at about 100 institutions in 18 nations. This was absolutely necessary for success because these gravitational wave detectors are so complex. In order to make these measurements of extremely small motions, in the presence of enormous numbers of different kinds of noise, you had to build instruments of huge complexity, and that required a huge range of talents of a variety of different scientists and engineers. From 2000 to 2010, we ran our initial interferometers. Then under the leadership of two subsequent directors, we installed our advanced interferometers, and by 2015, we were ready to turn on and begin our gravitational wave search. In the meantime, it was absolutely essential that computer simulations of collisions of black holes be brought to maturity because we were, or at least I was quite sure the first thing we would see would be colliding black holes, and we could not solve the equations for the black hole collisions with pencil and paper, only on computers. That was really difficult, but we had to be able to predict the shapes of the waves, the so-called waveforms, for comparison with the observations in order to be sure of what it is was the source of the gravitational waves. And so this also was a half-century effort on the experimental side from when Ray and I began to think about this, and a half-century effort on the computer science side by a whole other set of scientists. September 14, 2015, the advanced LIGO detectors, the second generation, was just preparing to begin its first search of gravitational waves when suddenly the first signal came in. 3 days before the first search was supposed to begin. The director of LIGO declared the first search has just begun, just a few minutes ago when the first signal arrived, and we were off and running. The first signal, the raw signal, and I'll use a technical phrase, only bandpass filtered to remove frequencies above 300 hertz and below 30 hertz. Otherwise, this is the raw signal. At Livingston, Louisiana, at Hanford, Washington, the same signal within the small amounts of noise. And when the signal was cleaned up and compared with the waveforms predicted by computer simulations, the computer simulations are a red line in here, the cleaned up signal is in gray, the agreement was essentially perfect. And from that comparison, we can go back to the simulations and see that what had happened was two black holes went around and around each other, collided and merged. The initial black holes weighed 29 times what the sun weighs, and 36 times what the sun weighs, or a total of 65 solar masses. Final black holes, 62 solar masses. 3 solar masses of mass is gone into gravitational waves, as I told you. And it came out so quickly, in about 1/10 of a second, that the total power output in that black hole collision, the energy per unit time, was 50 times larger than the power output in light of all the stars in the universe put together. 50 universe luminosities coming off in a burst of gravitational waves that we saw with LIGO. We have reported the discovery of six bursts of gravitational waves from black hole mergers. Here are the waveforms that came in for the six bursts, stretching, plotted up, squeezing, plotted down. And we have the masses and the distances to all of these, ranging from black hole masses from 8 solar masses to 36 solar masses, at distances from about 1.4 billion light years to 3 billion light years. This is what we saw over a period of several months of observation. It was very important to identify where the sources were on the sky so that electromagnetic astronomers could go and look to see whether there's any light or X-rays or radio waves coming from that source. And we had very poor angular resolution on the sky. These are error boxes on the sky for the first few signals, because our primary way of seeing where the direction of the source is the time delay in the arrival of the signal at different locations on Earth. And we had only 2 detectors. With 2 detectors, you can't triangulate on the full 2-dimensional sky. You have to have 3 detectors. Fortunately, last August, the Virgo gravitational wave detector, which is a French, Italian, Netherlands, Poland, Hungary collaboration with 250 scientists at 19 laboratories. That detector went into operation, and on the black hole merger that had occurred on August 14 of last year, the error box was much smaller on the sky, the size of a few times bigger than the moon, but that was good enough now to do a real deep search for electromagnetic emission, and none was seen. Remarkably, however, just a few days later, LIGO and Virgo observed gravitational waves from the collision of 2 neutron stars. Each of these stars has a diameter of about 20 kilometers, the mass of 1.5 times the mass of the sun. These stars collided and merged with a great burst of light, X-rays, radio waves, gravitational waves. This is what is called a kilonova, and kilonovas were predicted by theorists. This is the first detailed observation of a kilonova from collision of 2 neutron stars. 2 stars made essentially of pure nuclear matter. The gravitational wave signal here, which I will not discuss, followed 1.7 seconds later by a burst of gamma rays. Location of the gravity wave signal on the sky inside this little green box, thanks to the Virgo collaboration with LIGO, 3 gravity wave detectors. The gamma ray burst was from inside this bigger box. They didn't have as good an angular resolution. And then X-rays, ultraviolet, optical, infrared, and radio waves from a galaxy that was then identified sitting down here at that location inside both error boxes. It was really marvelous. It involved something like 15% of the world's astronomers observed this. It was the most observed event on the sky that humans have ever seen. This was the beginning of multi-messenger astronomy, each messenger being a different kind of radiation: X-rays, gamma rays, radio waves, light, gravitational waves. And the prediction is, from computer simulations, that collisions of neutron stars like this produce most of the gold and platinum that we see in the universe. For example, on Earth, the gold and platinum that we have here on Earth, almost all comes from colliding neutron stars that collided before the Earth formed. And the observations verified with moderately good confidence that that really was true, from looking at the spectra of the light that came off of this gravitational wave, off of this source. So let me then show you a few photographs of the instrumentation of LIGO, our gravitational wave detector. Barry Barish, the genius who really put the LIGO collaboration together and made this happen, likes to put a baseball player, an American baseball player in here so you can see it for size. Why he doesn't put a LIGO scientist there, I'm not sure, but that's his fault. These are the vacuum chambers in which the mirrors hang. This is LIGO as seen in Hanford, Washington, as seen from the air. This is one of the mirrors hanging it's hanging freely, but it has a big cage to protect it from falling if the wires break. And the gravitational wave comes on and pushes this mirror back and forth, I remind you, by 1/100th the diameter of the nucleus of an atom. These instruments, as I said before, are tremendously complicated. 100,000 data channels. They have a personality of their own that the experimenters must understand. It's very similar to Victor Frankenstein, who built his creature and only learned the personality of his creature after the creature came to life. The experimenters have to learn the personality of these instruments after they came to life. And they aren't behaving the way they're supposed to be behaving. That's why we're not at design sensitivity. And so LIGO and Virgo are now shut down for about 16 months with the experimenters doing experiments to learn the personalities of the instruments and coax them down toward their design sensitivity by about 2020, by which time they will see 3 times farther into the universe, a volume 3 cubed or 27 times bigger. That means instead of seeing 1 black hole merger per month, roughly, when the observations are being carried out, they'll be down to 1 black hole merger per day by 2020. And going into the future, also by 2020, then we should see, we expect gravitational waves from spinning neutron stars, from so-called pulsars, from black holes tearing neutron stars apart. We've already seen them, waves from neutron stars colliding. From the cores of supernova explosions, we should be able, with combined observations of neutrinos from the supernova cores and gravitational waves, to really diagnose how supernova explosions are triggered. And as I said before, there will be enormous surprises. All of these, except for the supernovae, I think are likely to be seen by 2020. I'm hopeful for some gigantic surprises by then. Supernovae are sufficiently rare that they will come along after some few more years. So, beyond advanced LIGO, if we're only limited by technology and not by money, by the early 2020s, we should have improved instruments that can see black hole mergers a few times per day. By the late 2020s, a 3rd generation of instruments that can see black hole collisions about once per hour. And by the 2030s, with another generation, seeing all the black hole collisions with masses less than about 1,000 times the mass of the sun in the entire universe, in the entire history of the universe. Enormous strides that we expect to have over the coming 15 years or so, 15, 20 years. There actually are 4 different windows, that is frequency windows for gravitational wave detectors, that we expect to be opened by the 2030s. This is as though we were opening or beginning optical astronomy, radio astronomy, gamma ray astronomy, and radio astronomy. 4 different forms of astronomy, all within a period of 20 years. LIGO has already opened up the gravitational wave window for waves that oscillate with periods of milliseconds. LISA, a European Space Agency mission with a spacecraft that track each other but with laser beams out in interplanetary space, will observe gravitational waves with periods of minutes to hours. A technique called pulsar timing arrays done by radio astronomers, I won't go into the details, should, within a few years, be seeing gravitational waves for periods of years to decades. And then there's a technique I'll talk about at the very end of my talk, looking for gravitational waves for periods of billions and hundreds of millions of years. Of course, that's longer than the life of a graduate student. And so this is a technique where you don't look at the oscillations of the waves, you look at the pattern of something on the sky, as I will explain at the very end. So, let me just say, in concluding, 2 things. I want to talk about exploring black holes with gravitational waves. And then I'm going to talk about exploring the birth of the universe with gravitational waves. These are the things that I'm most excited about, that gravitational waves are going to bring us. Using optical technology, using the technology of light as our fundamental technology in these gravitational wave detectors, these are the most exciting things we will explore in the coming few years. Black holes are not made from matter like you and I. Instead, they're made from warped space and time. And you can visualize it in this way. Take an equatorial slice through a black hole. That's a 2-dimensional sheet. that sheet is not flat like a flat sheet of paper. It's curved. And in order to visualize the curvature, you can imagine embedding it in a higher dimensional space, which is sometimes called by physicists the bulk. And if you do that, then our universe, which is nearly flat, is out here far away. And near the black hole, this goes down, as seen from the bulk, into a trumpet horn or a whirlpool type shape. The color coding is the slowing of time, where you see yellow, time is flowing at 10% the rate it is back here on Earth. And the arrows are the dragging of space into motion by whirling motion by the spin of the black hole. And so these are the three things that we see as aspects of warped space-time for a quiescent black hole. The warping of space, the slowing of time, and the whirling motion of space around the horizon. The horizon of the black hole, the surface, is this circle down here, the black circle, where time slows to a halt. But that's not really a circle. Remember, I'm looking at a two-dimensional surface through the black hole, an equatorial slice. And if I restore the third dimension, that circle becomes a flattened sphere. So the horizon, the surface of the black hole, is a flattened sphere. Now, LISA, as I told you, is three spacecraft that track each other with laser beams with separations of about 5 million kilometers, looking at gravitational waves with periods of minutes to hours. This is the ideal period of gravitational waves that is emitted by very massive black holes weighing millions of times what the sun weighs. So one of the things that we expect to do with LISA is to look at the gravitational waves from a small black hole going around one of these very huge black holes, gradually spiraling in. And as this gravitational waves over a period of a year goes around, as the small black hole goes around the big black hole over a period of a year, the gravitational waves that it emits carry a detailed map of the entire space-time geometry of the big black hole that's being explored by the little black hole as it travels around. So one of the things we expect to do is to map the warping of space and time of a big black hole, just like NASA and ESA map the surface of Mars, the surface of other planets. But here you're mapping the curvature, the shape of space and time around a black hole. We also expect to, in fact we've already begun to, study the dynamics of warped space-time triggered by colliding black holes. When the two black holes collide, they create a veritable storm in the shape of space and time. And it's that storm that, like a storm at sea, a giant storm at sea, that generates the gravitational waves that we see. And so I'm going to show you then from a simulation, a computer simulation, of the source of the first gravitational waves that LIGO observed, what that looked like. And I showed you what it would look like to our eyes as the two black holes went around and around each other at the very beginning of this talk. I'll now show you what it would look like to a being, a bulk being who lives in the bulk, lives in a higher dimension, looking in on our universe, again with one dimension of our universe removed. So you see these two funnels, these are the two black holes, as they go around and around each other. The color coding is the slowing of time, the arrows are the dragging of space into motion. And this has gone into slow motion, and a gigantic splash, like in a storm at sea, a huge distortion of space, and a slowing of time in the dark red, and then an oscillation with the gravitational waves going propagating out. That's the dynamics of the shape of space and time that a bulk being would have seen looking in on our universe when those two black holes collided. And we are now in the process of exploring that dynamics of warped space-time by a combination of computer simulations, comparing those with the gravitational wave observations. As I said, we already have 6 black hole collisions to use for these explorations, and again, comparing the observations with the theory. Finally, I want to talk about exploring the birth of the universe with gravitational waves. I'll begin with the birth of the fundamental forces, and then I'll go to the very birth of the universe. When the universe was about 1/trillionth of a second old, predictions from the fundamental laws of physics say that the electromagnetic force was born. It didn't exist before then. Before then, the universe was so hot and so dense, so extremely hot, that the electromagnetic force was combined with the weak nuclear force into a unified electroweak force that obeyed laws that are very different from what electromagnetism now behaves, very different from the so-called Maxwell equations. But age 10 to the minus 12 seconds, as the universe expanded and cooled, the forces were born, were separated, the electroweak force and the electromagnetic force, the weak nuclear force and the electromagnetic force came apart, quite possibly inside bubbles like water droplets condensing out of water vapor. This is, if this was like this, then it's a first-order phase transition, and what I'm going to tell you depends on this being a first-order phase transition. Unlike water droplets that form, that just hold their shape, in this case, the droplets with the new electromagnetic force on the interior expand at nearly the speed of light, collide, merge, and produce a burst of gravitational waves that travels out into the universe. The universe, as it expands in the era after that, up until the day, it stretches those gravitational waves until the day they are in LISA's frequency domain. So LISA, one of LISA's primary goals, the European Space Agency's mission LISA, is to watch the birth of the electromagnetic force in this way through these gravitational waves. Finally, there's a prediction that primordial gravitational waves from the very birth of the universe should have been created and should be observable within the next few decades by two different techniques. The birth of these waves is in the so-called Planck era, the Big Bang. The gravitational waves are produced very, very weak initially, possibly only what are called vacuum fluctuations, the minimum strength of gravitational wave that's possible. But then the era of so-called inflation should have amplified those waves enormously. Those waves should have traveled outward as the universe expanded. When the universe was 380,000 years old, and the plasma was recombining, electrons and protons were combining together to form hydrogen atoms. These gravitational waves should have, and at that moment, what we now see as cosmic microwave radiation was being created. Those waves of gravitational waves, by stretching and squeezing the plasma, should have placed a polarization pattern onto these cosmic microwaves. That cosmic microwave polarization should be observable in our universe today. The wave spectrum of the gravitational waves that we see indirectly in this way is a convolution, a combination of whatever came off of the Big Bang with inflation. And so I find it very exciting to contemplate the possibility that the standard prediction of what came off the Big Bang, so-called vacuum fluctuations, is wrong, and when these waves are actually observed, it will be something else. We will thereby be probing the birth of the universe, the era in which the laws of physics were the laws of quantum gravity. Those laws of quantum gravity are the holy grail of theoretical physics today. By 2050, we hope to have a mission called the Big Bang Observer, that's a successor to the LISA mission, that can observe directly these primordial gravitational waves at periods of seconds. So we will be able to see the birth of the universe in two very different frequency bands and see whether or not the standard predictions are correct. So let me conclude by reminding you that 400 years ago, Galileo built his first little optical telescope, pointed at the sky, saw the light from the four moons of Jupiter, saw the light coming in from the craters on our moon, and initiated electromagnetic astronomy. 2 years ago, LIGO detected its first gravitational waves from colliding black holes, and thereby created gravitational astronomy. The laws of physics say that there are only two kinds of waves that can be created in the distant universe and propagate through the universe, bringing us information about what's going on far away: electromagnetic waves and gravitational waves. When you contemplate what a revolution there has been in our understanding of the universe using electromagnetic waves since Galileo 400 years ago, then I invite you also to contemplate what kind of revolution gravitational waves and electromagnetic waves together will bring us over the next 400 years.